Okay, let's jump right into this explainer on chemical energetics. We're going to unpack exactly how energy is stored, transferred, and mapped during chemical reactions. Have you ever wondered what is actually happening on a totally atomic level when something bursts into flames? Or on the flip side, when a chemical ice pack suddenly turns freezing cold in your hands? Well, it is all about the invisible flow of energy.
We interact with these chemical reactions literally every single day. I mean, we know that breaking down or combining invisible molecules can warm our hands on a freezing winter walk or ice our injuries after a tough workout. But to really grasp why some of these reactions blast out heat while others completely suck it in, we need to look under the hood.
So here is our roadmap for today's explainer. First, the energy exchange. Second, exothermic versus endothermic reactions. Third, mapping those pathways. And finally, breaking and making bonds.
Let's start with part 1, the energy exchange. We need to establish the ground rules.
You probably know the golden rule of chemistry, right? Energy cannot be created or destroyed. It can only be transferred. To track this, we divide the entire universe into two distinct zones. First, we have the system. You can think of this as the VIP section. It's the actual chemical reaction itself, where the bonds act as tiny stores of chemical energy. Second, we have the surroundings. And this is literally everything else in the universe. The beaker, the air in the room, the thermometer you're holding. Actually, fun fact, technically, even a star exploding in the Andromeda galaxy is considered part of the surroundings.
Moving right along to section 2, exothermic versus endothermic from a macro perspective. Take a look at the arrows on these two flasks because it perfectly captures the contrast here. On the left, we've got an exothermic reaction. The system, those chemicals inside, is losing energy, shooting thermal energy outward into the surroundings. If you held that flask, the temperature of your hands, which are the surroundings, is increasing, so it feels hot. Now look at the right, an endothermic reaction. This system is actively absorbing heat inwards from the surroundings just to make the reaction happen. Because it's literally stealing heat from the environment, the temperature of the surroundings drops. That flask would feel completely cold to the touch.
If you're studying for an exam or honestly just want a bulletproof way to remember this, rely on this simple tip. Just focus on the prefixes. Exothermic means heat exits the system, making the surroundings feel hot. Endothermic means heat enters the system, making things feel cold.
And we take advantage of these exact energy transfers every day. A self-heating coffee can uses a built-in exothermic reaction in the base to rapidly warm up your drink. Combustion, like burning methane and oxygen, is also highly exothermic. On the flip side, those sports injury cold packs, they rely completely on endothermic reactions. You snap the pouch, the chemicals mix, and boom, they immediately begin pulling heat away from your swollen ankle to fuel the reaction. Thermal decomposition, like using a Bunsen burner to break down solid calcium carbonate, is another classic endothermic process, simply because it requires a constant supply of heat to keep going.
All right, on to section 3. Let's map these reaction pathways and actually graph the heat.
Look how visually obvious the energy loss is on this exothermic reaction pathway diagram. On the y-axis, we're tracking the total energy of the molecules, and the x-axis shows the reaction progressing over time. Notice exactly where we start. The reactants have a specific amount of stored chemical energy. But because thermal energy is transferred out to the surroundings during this exothermic reaction, the final products end up significantly lower on the chart. They literally have less energy at the end than they did at the beginning. The system's loss is the surroundings' gain.
Now flip that around for this endothermic reaction pathway. It is the exact opposite visually. The reactants start low on the y-axis. Then, as the reaction progresses, the system gulps down a massive amount of thermal energy from the surroundings. This forces the final energy level of the products way higher up the chart. The system has gained energy overall.
But wait, did you spot that initial upward curve present on both of those diagrams? That little bump represents the activation energy, often written as EA. This is the mandatory hurdle, the initial push required to get absolutely any reaction going. For particles to react, they have to physically collide with each other with enough force and the perfect orientation. The activation energy is that bare minimum requirement. Think of it like lighting a match. Even highly exothermic fuels like wood need that initial spark of heat to start burning. The greater that initial rise on our graph, the more energy you need just to kickstart the whole process. So the ultimate goal in measuring all of this is calculating the overall difference between the start and the finish. We call this the enthalpy change, represented by the symbol delta H. For an exothermic reaction, because the system loses energy to the surroundings,
delta H is a negative value. For an endothermic reaction, because the system absorbs energy, delta H is positive. That single number tells us the net thermal result of the entire chemical event.
Finally, Section 4, breaking and making bonds. Let's zoom way down to the micro level.
So why do elements even bother reacting at all? Well, they're chasing a stable energy state, usually by trying to gain a full outer shell of electrons. But to achieve that, they have to play a crazy chemical tug-of-war. Breaking stubborn, existing bonds is incredibly hard work and requires pulling energy in from the surroundings. Therefore, bond breaking is strictly an endothermic process. However, when atoms finally snap together to make new, stable bonds, they release energy outward. So bond making is strictly an exothermic process. And here's the kicker. Every single chemical reaction features both of these steps happening at the exact same time.
If you want to mathematically prove if a reaction is going to be exothermic or endothermic overall, you just have to figure out which side of the tug-of-war is stronger. You just follow these 3 steps. First, write a balanced equation. Second, figure out exactly which atomic bonds are present in both the reactants and products. Every specific bond has a known numerical bond energy. Finally, you calculate the total energy spent breaking the old bonds and compare it against the total energy earned making the new bonds. If you release more energy making the new bonds than you spent breaking the old ones, the reaction is exothermic. But if you spent more energy breaking those stubborn old bonds than you got back forming the new ones, your reaction is endothermic.
As we wrap up this explainer, I just want you to pause and ponder the sheer magnitude of what we've covered today. The simple act of atoms rearranging themselves dictates the flow of heat in our universe, from the ice packs on our knees to the combustion engines in our cars. So, if all chemical bonds act like tiny, locked energy stores, just think about how much untapped thermal power is hiding in the everyday molecules surrounding you right now. Thanks for joining me on this deep dive into chemical energetics, and keep questioning the invisible forces that shape our world.